We're talking about discretization. We kind of derived things in the previous video. Discretization means how do you go about approximating a continuous time system where this input, and we're only worried in the state process equation, state equation. How do you approximate this in continuous time with a discrete time model? We're going to assume that the input is zero mean unity white noise in the continuous time version. This U is zero mean unity white noise. And discretization pretty much boils down to finding two things in this model. This phi and this Q, which is this expectation or this covariance matrix or this input of the discrete time model. We really don't deal with this measurement equation just yet. So we had these formulas, a way to do it. There was a way to find the phi using inverse Laplace transform, and the way to find the Q, especially for F and G constant, which was this little integral here. So now let's do an example. Here's our system. Our job is to discretize it. Starts out with unity white noise. That's good. Was our assumption. Going through this little transfer function to give the output we call x2, which is going to be a Gauss-Markov process. And then that x2 is going to be integrated to give us x1. So and here we have an integrated Gauss-Markov process, and we call the output y. This scalar thing we observe. Even though this is single input, single output, we're going to deal with it in state space format, state space representation. So let's go through this. What does this transfer function mean? That means x2 in the Laplace domain is that transfer function times the Laplace transform of this guy. If you do a little algebra, we'll bring this s plus beta over on the left. Means that, so I can rewrite that equation. And what does this mean? Multiplying by s means taking the derivative. I can move this to the right side. Here's what it means in the time domain. x2 dot, or the derivative of x2 minus beta x2 plus this thing times u. And what does this thing mean? It's x1 equals 1 over s x2, or s times x1 equals x2, or in the time domain, x1 dot equals x2. We have these two equations for x1 and x2. We can put it in matrix form. x1 dot equals x2. Here's that. And x2 dot equals this minus beta x2, okay, plus this thing times the input. So here is the state equation. In this case, the measurement equation would be the only thing measured is x1. So this, we don't need to deal with this with our little discretization exercise. So anyway, we now have the state space representation. We can now start the discretization process. Here's where we left off. Remember, the two big things you do are find phi and find q. Finding phi, we had this little formula. It was the inverse Laplace transform of this guy, si minus f, inverse. Here was the f, 0, 1, 0 minus beta. Si minus f, what is that? It's all s's on the diagonal minus the f. So you'll have a minus 1 up here and a plus beta over there. So that is Si minus F. You need to take its inverse, so you need to know how to take the inverse of a 2 by 2. You divide by the adjunct. No, you divide by the determinant. The determinant. The determinant is product of the main diagonals minus the product of the off diagonals, which is S times S plus beta here. And how do I get this part? I switch the main diagonal terms, so the S plus beta goes top left, S goes bottom right, and I switched just the signs of the other two paths. So this will become a +1, and this is a 0, so it stays a 0. Now if I bring this inside, here's what all that looks like if you put it all in one matrix. I can break this guy up using partial fraction expansion. And from here, I can look up every term in a Laplace transform table and find the Laplace transforms in terms of a generalized tau. When I want this phi sub k, all I'm doing is plugging in the time step for the tau. So here is phi sub k. And you'll see it doesn't depend on what k is, just what the time step is. And that's what you're always going to get when this f is constant. So we found the phi. Now we got to find the q. Well, that really means we need to find this. What is that? We have the phi and we have the g. We just did previous charts. So we need to do all this matrix arithmetic, all this matrix multiply. Easy way to do it, and an easier way to do it. First find this matrix multiply, and then multiply it by its own transpose. So let's see, what is just these two guys? It'll be 0 plus this guy over beta times that. This will be 0 plus e to the minus beta t. So there's that. Here's its transpose. Now do this matrix multiply. I don't want to go through that pain, but here's what you get. And the q, then, is the integral of this mess as you integrate from 0 to t, the time step. Not quite done yet. So we need to take this integral, which means we need to take actually 4 different integrals. And I'm not going to go through this pain on the video, but each one of these involves pieces that look something like this with these little results. Put all that together, here's what you get. And yes, this was rather tedious. That's why I'm not going to go through it. But it's very doable. You should be able to do this. It's just a little time consuming. So we have the q. And it doesn't depend on k. And the phi and the q will not depend on k as long as both f and g are constant. It always happens. And that's all I made my students do, just because everything else got a little bit more ridiculously tedious. So that's one example of the basic process of discretization. I'll do another example in another video.